Hello, this is Mrs. Sargent, and this is lesson 8.5, Stoich and Solutions. So we are finishing up our solutions unit by looking at how stoichiometry and solutions chemistry interact. So here we have three different solutions. All three solutions have a molarity of 3. So C6H12O6, this is sugar, and this is a covalent compound. Sodium chloride is table salt, and this is an ionic compound. And calcium chloride is also an ionic salt, not table salt, but another type of salt. So remember that covalent compounds and ionic compounds, they have different methods of dissolving. Covalent compounds are going to dissolve whole. Where ionic compounds are going to split into the ions. So when we dissolve in these two different methods, it's going to affect the number of moles per liter of solution. So here, because sugar dissolves whole, we are going to have 3 moles of our C6H12O6 molecules. Sodium chloride is going to split into sodium ions and chlorine ions. So there's only one of each of these ions in our chemical formula. So we are going to have 3 moles of our sodium ions as well as 3 moles of our chlorine ions. However, when we get to calcium chloride, this is going to split into calcium 2 plus ion and 2 Cl1 minus ions. So we have 3 moles of our calcium ions and 3 times 2 gives us 6 moles of our chlorine ions. So you can see down here in the picture we only have 3 of our glucose molecules. Here with our sodium chloride we have 3 of our sodium ions and 3 of our chlorine ions. And then with calcium chloride we have 3 calcium ions, but we have 1, 2, 3, 4, 5, 6 chlorine ions. So the number of ions per formula unit is going to change the number of moles per liter of solution. So for a given solution, are the concentrations, the molarity of the ions, going to be the same as the concentration of the salt as a compound? And the answer to this would be no, not always. Here, when we look back, our number of moles of our sodium ions and our chlorine ions match the number of moles of our compound as a whole. But when you have more than one ion per compound or per formula unit, your molarity, your number of moles per liter, is not going to match that of your compound. So in a solution of potassium sulfate, the first thing that we want to do is we want to write out what the dissociation equation is so that we know what ions we are working with. So potassium sulfate is going to split into 2 potassium ions and 1 sulfate ion. So we're going to calculate the moles of our compound in a liter solution, the moles of our potassium ion in 1 liter solution, and the moles of our sulfate ion in 1 liter solution. So we're given 1 liter. So remember, we always start with the number and unit that is given to us in the problem. So that is what we're starting with. Molarity equals the number of moles per liter of solution. So we know our molarity is 2.50 molar. And we also know that we have 1 liter of solution. So if we cross multiply and we solve for n, we're going to get 2.5 moles of our compound per liter of solution. So 2.5 moles of potassium sulfate per 1 liter of solution. So we can cancel out liter, and our moles is exactly the same. So if we had a different volume that we were given, we wouldn't end up with the same number of moles, and that's what we're going to look at down here at the bottom. So to find the moles of our potassium ion, again, we're going to start with the 1 liter that is given to us in the problem. We're going to use our molarity, the 2.5 moles of our compound, potassium sulfate, per 1 liter. And then we're going to look at our dissociation equation for our mole-to-mole ratio. So in our dissociation equation, we have 1 mole of potassium sulfate but we have 2 moles of our potassium ions. So we can cancel out liters and we can cancel out moles of potassium sulfate. So essentially we need to take 2.5 and multiply it by 2, which is going to give us 5 moles of our potassium ion. And then to calculate the moles of our sulfate ion, we start with 1 liter. That is given to us in our problem. Using our molarity, the 2.5 moles of potassium sulfate per 1 liter. And then looking at our dissociation equation, we have 1 mole of our sulfate ions per 1 mole of our compound. So we just have 2.5 moles of our sulfate ion. So this are moles of our compound, the moles of our ion that we only have 1 of in our dissociation equation is equal basically to our molarity. But what happens when we change the volume of our solution? So Here we are given 45 milliliters of solution, and we want to know the moles of our potassium ions. I just needed a little bit more room. Okay, so we're starting with 45 milliliters, which when we convert this to liters is going to be 0.045 liters. The moles per liter is still 2.5 moles of our compound. Per 1 liter of solution. And then looking at our dissociation equation, we have 1 mole of potassium sulfate, but we have 2 moles of our potassium ions. So we need to take 0.045 times 2.5 times 2, and you should get 0.225. There should be 0 after that. 0.225 moles of our potassium ions. So we can see that when we have a different starting volume, that's going to change the number of moles of our ion. So the concentration of ions in solution. Molarity concentration are calculated by moles per liter. This is often written with a bracket around your compound or your ion symbol and equal to the molarity number. So this can be a formula unit like sodium chloride, or it can be individual ions like our sodium ion, or our chlorine ion. Sorry, I don't know what's wrong with my stylus. It's not picking up very well tonight. So you can have 1 mole of your compound, but when it dissociates, the mole ratio of your ions to formula units may give you a different concentration of that ion in particular. So you need to check the coefficients in your dissociation equation. So whenever we're trying to find the concentration of our ions, we always want to do the dissociation equation. So for strontium chloride, when we put that into water, we're going to separate it out into strontium ions. Strontium 2 plus aqueous, and we have 2 chlorine ions that are also going to be aqueous. So here we have 1 molar strontium chloride. If no volume is given, you can assume 1 liter. So first we need to find the moles of our compound. So if we have a 1 molar solution, and we said that we are going to assume that we have 1 liter of solution, our number of moles is going to be 1 mole of our compound. So if we have 1 mole of strontium chloride, in our equation, our dissociation equation, we have 1 mole of strontium chloride. And we have 1 mole of our strontium ions. That's going to give us 1 mole of our strontium ions. To find the concentration, we need to divide by the volume, which is 1 liter. So the concentration of our strontium ions is 1 molar, because 1 divided by 1 is going to give you 1 molar. So then to find the moles of and molarity of our chlorine ions, again, we're starting with 1 mole of our compound. But in our dissociation equation, we have 2 moles of our ions, chlorine ions. So this is going to give us 2 moles of Cl1 minus. Divide by our volume of 1 liter, the concentration of our chlorine ions is 2 molar. Okay. So we have a couple more examples. Well, I'll talk about the steps for finding the concentration of the ions and then a few more examples with that. So how to find the concentration of ions. First, you want to write out the dissociation equation. Then you want to find the moles of salt of your salt compound. From that, you can find the moles of your ions. If you are given a volume in milliliters, you need to convert it to liters, and then you use your molarity equation to find the concentration of your ions. So aluminum chloride is going to split into aluminum ions, Al3+, and 3 chlorine ions. Okay, so we have 15 milliliters of our 2 molar aluminum chloride solution. So in our molarity equation, we have 2 molar and our volume 15 milliliters, move your decimal 3 places to the left, is 0.015 liters. So to find our number of moles, we need to take 2 times 0.015 and that is going to give us 0.030 moles of our compound. So starting with our number of moles of our compound, then we can use our dissociation equation to find the moles of our ions. So we have 1 mole of our aluminum ion to every 1 mole of our compound. So our aluminum ions, we have 0.030 moles of our aluminum ions. So we found the moles of our ions. We already know our volume in liters. So I'm just going, since molarity is the number of moles divided by the volume in liters, I'm going to take this moles and divide it by our liters, 0.015. liters, and the concentration of our aluminum ion, 0.03 divided by 0.015, should give us a molarity of 2 molar. Now do the same thing for our chlorine ions, 0.030 moles of our aluminum chloride for every 1 mole of aluminum chloride. We have 3 moles of our chlorine ions. So 0.03 times 3 is going to give us 0.090 moles of our chlorine ions. Divide by our volume, which is 0.015 liters. And the concentration of our chlorine ions, 0.09 divided by 0.015, should give us 6 molar. So at this point, we've done a couple examples. In class, we split up and we did these problems. I would go ahead and pause the video, give these 2 examples a try on your own, and then come back and check them. Welcome back. So we have 0.0360 liters of a 1.5 molar ammonium carbonate solution. So we're going to start with 0.0360 liters. And sometimes I just like to set this all up as one calculation. So we know our molarity is 1.5 moles of ammonium carbonate per 1 liter of solution. I skipped over writing out the dissociation equation, so I'm going to go back and do that because I don't know what my mole to mole ratio is without taking a look at that. So my bad. So we have ammonium carbonate, and it's going to split into 2 ammonium ions and 1 of our carbonate ions. So for every 1 mole of our compound, ammonium carbonate, we have 2 moles of our ammonium ions. So 0.036 times 1.5 times 2 is going to give us 0.108 moles of our ammonium ions. Divide by our volume to find the molarity, or the concentration, of our ammonium ions. So 0.108 divided by 0.036 gives us a concentration of our ammonium ions to be 3 molar. So now we need to do the same calculation for our carbonate ions. Starting with our starting volume of 36 milliliters, or 0.036 liters. For every 1 liter of solution, we have 1.5 moles of ammonium carbonate. We have 1 mole of our carbonate ions per 1 mole of our compound. So 0.036 times 1.5 should give us 0.054 moles of our carbonate ions. Divide by our volume of 0.036 liters, and we should get a concentration of our carbonate ions to be 1.5 molar. So that's our first example. Our second example, with 250 milliliters, convert this to liters. So we have 0.250 liters. Of our solution. That is a 6 molar solution. So for every liter of solution, there is 6 moles of sulfuric acid. And again, got to go back and get our dissociation equation done. This is usually the point where I remember that, oh yeah, I need to do that. But, so we have 2 moles of our hydrogen ions and 1 mole, oh my gosh, this thing has a mind of its own, of our sulfate ions. So 2 moles of our hydrogen ions to 1 mole of our compound. So 0.25 times 6 times 2 should give us 3 moles of our hydrogen ion. Divide by our volume of 0.250 liters. And the concentration of our hydrogen ion is 12 molar. For our sulfate ion, we have 6 moles of our compound per liter. For every 1 mole of our compound, we have 1 mole of our sulfate ion. So 0.25 times 6 times 1 is going to give us 1.5 moles of our sulfate ion. Divide by our volume of 0.25 liters. 1.5 divided by 0.25 is going to give us a concentration of our sulfate ion to be 6 molar. So those are those 2 examples. So the molarity equals moles per liter, and that can be used as a conversion factor in our stoichiometry calculations, which is what we've already been doing. If we're given a volume, we can use molarity, moles per liter, to find the moles. Mole to mole ratio, we can find moles of a new compound or ion, and then we can use the molarity to find the volume of that in solution. So zinc reacts with hydrochloric acid to produce hydrogen gas and zinc chloride. So how many liters of a 1.5 molar hydrochloric acid solution completely reacts with 5.32 grams of zinc? So we're going to start with our 5.32 grams of zinc, because remember that our molarity, this is 1.5 moles per liter. So this is actually a conversion factor and not our given. So 5.32 grams of zinc. So we need to go from grams to moles by using the molar mass of zinc, which you should find to be 65.41 grams. Use our mole to mole ratio to go to hydrochloric acid. So for every 1 mole of zinc, there are 2 moles of hydrochloric acid. And then this is where our molarity is going to come into play. We finished our mole to mole ratio. Now we're going to use liters over mole to find the volume of, in liters, of our hydrochloric acid solution. So 1 liter equals is equal to 1.5 moles of hydrochloric acid. So we can cancel out grams of zinc, and moles of hydrochloric acid. So we need to take 5.32 times 2 and divide it by, in parentheses 65.41 times 1.5. And we're going to need a volume of 0.108 liters of our hydrochloric acid in order to completely react with this mass of zinc. Similarly, how many grams of zinc can react with 225 milliliters of a 0.2 molar? So again, this is our conversion factor. The milliliters, which we need to convert to liters, which is 0.225 liters. So 0.2 moles per 1 liter. And then we're going to use our mole to mole ratio. So we have 2 moles of hydrochloric acid in our equation. And we have 1 mole of zinc. And then to go from moles to mass, we need our molar mass of zinc, which is 65.41. We can cancel out liters, we can cancel out moles of hydrochloric acid and moles of zinc. So we need to take 0.225 times 0.2 times 65.41 and divide that by 2. And we would need 1.47 grams of zinc. Okay, so 2 examples going from grams to liters or going from liters to grams. With this last example, I would go ahead and pause the video and give this a try on your own. Welcome back. It asks for how many milliliters of a 0.25 molar barium chloride solution would need to react with 32.5 milliliters of a 0.16 molar sodium sulfate solution. So the 32.5 milliliters, that is what we are starting with. Except we need to convert it to liters. So 0.0325 liters. 0.160 molar sodium sulfate solution, so that we know that this is 0.160 moles of sodium sulfate per 1 liter. Looking at our chemical equation, we have 1 mole of sodium sulfate in our equation, and we want to go to barium chloride. We got 1 mole of that in our equation as well. And to go to a volume of barium chloride, we're going to use our molarity as a conversion factor. So we have 0.250 moles of barium chloride per 1 liter. So we need to take 0.0325 times 0.16 and divide it by 0.25, which is going to give us 0.0208 liters. So that's our volume in liters, but we're asked to state our volume in milliliters. So we need to convert liters to milliliters. So multiply by 1,000 or move your decimal 3 places to the right, which would give us 20.8 milliliters. Okay, that is it for Stoich and solutions on the first day. If you have questions, please stop by and see me. Thanks. Have a great day.